Good evening. Good evening. I'm Dick Meserve, the president of the Carnegie Institution for Science, and it's wonderful to see you all here for a capital science lecture. This evening's lecture is being sponsored not only by Carnegie, but also by the Delegation of the European Union, the United States, the Embassy of Austria, and the Embassy of Switzerland. We're very much pleased joining forces with them for what I'm sure is going to be a very interesting evening. I'm going to ask that Ambassador Valda Almeida, who is the ambassador representing the delegation of the European Union to the United States, to say a few words of greeting, and then I'll return to the stage to introduce our speaker. Your Excellency.
Thank you very much. First of all, good evening, Happy New Year. Still early enough in the year to be able to continue to say so. Make sure that it is really a good year of 2014. It's a great pleasure to be here. I must confess it's my first time. I'm impressed by the room. I'm impressed by the audience. I'm impressed by the amount of knowledge that is united here tonight. And so on behalf of the European Union, welcome to this event. My daily life doesn't deal too much with science, and I'm very happy about that. I deal with politics, diplomacy, trade, and things like that, where, most of the time we have to deal with confrontational situations where not always we have an agreement, and across the Atlantic we have to find our consensus. There is one area in which I think we can say there is a consensus, is on the need to join efforts around science, innovation, research, to the benefit of mankind. And I think this is the most noble aspect of scientific activity that unites us here tonight. We are paying tribute to Professor Dingwell, who is in himself an incarnation of the transatlantic spirit. I mean, he's a dual citizen of Canada and Germany, and we were talking a little bit just before, I think he's also a citizen of Portugal, where I come from, because he was born in Newfoundland, where many years before him, many Portuguese were around, and he visited the Azores in his scientific capacity, looking at the Azorean volcanic activity, and he told me that he found people that looked very much like his mother. And so I think Professor is a real citizen of Europe as much as he is a citizen of Canada, with strong links with the United States. But more important than that, I dare to say, he's been a champion of international research partnership, and particularly in his service to the European Union. He has promoted basic science, international scientific cooperation, and his work has been outstanding, and I would like to pay tribute to that on behalf of the European Union. He worked as the Secretary General of the European Research Center in Europe, he contributed immensely to what is one of our priorities in Europe, is to, through research, through scientific activity, through innovation, promote the quality of life of our peoples, find solutions for our problems, move forward, creating jobs, promoting economic growth, the well-being of our societies. And I don't think that the role of scientists in doing this is valued enough in the political world, to be very frank. And I think it's important in this occasion to do this. In a way, Professor Dingwell embodies the ideal of transatlantic collaboration in science, technology, research, and innovation. And this has been exemplified many times throughout history. I could refer to a number of examples where European and American scientists together progressed in knowledge, in understanding. And I think we should, in times of difficult economic conditions, we should again look at this as a priority for political action, a priority for financing, and a priority for cooperation among governments. That's what ERC does in Europe. To give you just a few figures, the ERC has committed about $9 billion to over 4,000 world-class researchers since 2007. These include 58 different nationalities, 8 Nobel laureates, 3 Fields medalists, and the winners of many more internationally recognized prizes. By far, the largest group of non-Europeans benefiting from ERC grants comes from the United States, with about 45% of all foreign grantees. The work that is being done by the ERC, and Professor Dingwell played a major role in all this, is now funded by the European Union new program called Horizon 2020, a program for research and innovation for the next 7 years. It's a brand new initiative just launched in December. It commands a budget of more than $100 billion, $100 billion from 2014 to 2020. It will hopefully enhance EU competitiveness, create jobs, and tackle some of society's biggest challenges today. This is a budget which is 30% higher than the previous program you may have heard about, the 7th Framework Program. So in spite of budgetary difficulties, in spite of economic problems, we are putting 30% more money into research and innovation than in the previous because we believe that research and innovation is the only way to secure long-term prosperity for our citizens in Europe. It will be an open program. It's not reserved for Europeans, far from that. It will be the most open large research program in the world. And I want you to be aware because I want you to benefit from it as well. So many scientists in the room and people with public authority responsibilities, there are opportunities out there, and my colleagues in the delegation dealing with science are more than ready to help you doing all that. But tonight we are talking about volcanology, if I say it rightly in difficult word in English, and we are here to listen to Professor Dingwell. I'm sure that we will see an eruption in the amount of research cooperation across the Atlantic, inspired by Professor Dingwell. I want to thank him for all the efforts, thank him for the contribution he's given to the European Union, to European research, but also to cooperation across the Atlantic between Portugal and Newfoundland, and between many other places across the Atlantic. Thank you very much, and I'm sure we will have a wonderful evening listening to you. Thank you again.
Thank you, Mr. Ambassador. We can hope that your story about science funding in Europe inspires some of the people up the street here. The late British geologist Derek Ager famously wrote in 1973 that the Earth's history is much like the life of a soldier, a life in which long periods of boredom are separated by short periods of terror. The Earth similarly is shaped by boring events that are uniform and gradual, like the slow erosion of mountains, and terrorizing events that are abrupt and catastrophic, like volcanic eruptions. Volcanic eruptions are, of course, the result of deep Earth processes that shift the tectonic plates at the Earth's surface over time. There are about 1,500 active volcanoes on Earth today. Active usually meaning that a volcano has erupted within the last 10,000 years. And most of these volcanoes are concentrated around the Pacific Ring of Fire. About 50 erupt each year. Well, most volcanic eruptions have only local effects. Some have global impacts. The gas and ashes they send into the atmosphere form clouds around the world, blocking light and bringing cooler temperatures. The large 1815 eruption of the Tambora volcano in Indonesia, for example, caused snow to fall across the United States in July of the following year. 1816, the year without a summer, was an agricultural disaster for the United States. In Earth's past, volcanoes have led to even more massive geologic and biologic change. There's general agreement that there have been at least 5 major extinction events in Earth's history, perhaps many more, and volcanism is among the expected causes for several. Work by Lindy Elkins-Tanton, the director of our Department of Terrestrial Magnetism, and her colleagues, it shows that one of the most devastating extinction events, which occurred about 250 million years ago, was triggered by contemporaneous volcanic eruptions in Siberia, releasing gases that resulted in highly acidic rain. It resulted in the loss of more than 90% of marine species and 70% of terrestrial species. A study published last year, led by DTM fellow Terence Blackburn, found that the best evidence to date for massive volcanic eruptions massive volcanic eruptions were responsible for the extermination of half of Earth's species about 200 million years ago in another catastrophic event. Sometimes scientists also suggest that certain eruptions that occurred 65 million years ago in what is now India were the smoking gun that killed the dinosaurs. And that the asteroid that hit the Earth at about the same time was merely an added stress. We should not rest in the comfort that massive volcanic events are a thing of the past. As our guest tonight, Dr. Donald Dingwell, said, it is just a matter of time for where the next big one arrives. Yellowstone National Park, for example, sits on top of one of the Earth's largest supervolcanoes, a supervolcano that is statistically overdue for a massive eruption. Donald Dingwell is one of the world's premier volcanologists. He has been instrumental in transforming, as he expresses it, the awe one experiences during volcanic eruptions into a fully quantitative modern scientific area of investigation. His experimental work on the frontier of volcanology has led to new understanding of the properties of magmas and the processes by which they surface in explosive eruptions. Last year, he and his colleagues constructed the first ever lab-made volcano to simulate lightning flashes that are seen in real-life eruptions. Dr. Dingwell received his undergraduate degree in 1980 from the Memorial University of Newfoundland and his PhD degree from the University of Alberta. He then spent 2 years at Carnegie's Geophysical Laboratory as a postdoctoral fellow before accepting a position at the University of Toronto. In 1987, he was recruited to Germany as assistant to the director of a newly funded research institute in Beirut. Germany is still the home to Dr. Dingwell. In 2000, he was recruited to be the chair of mineralogy and petrology at the Ludwig-Maximilians University in Munich. There he founded and currently directs the Department of Earth and Environmental Sciences. He has received many awards. He received the Norman L. Bowen Award of the American Geophysical Union, the Otto Schott Research Award of the Ernst Abbe Fund, the Robert Wilhelm Benson Medal of the European Geosciences Union, the Victor Moritz Goldschmidt Award of the German Mineralogical Society, the MSA Award of the Mineralogical Society of America, and the Gerhard Hess Research Prize of the German Research Council. It's truly amazing. Just last year, the President of Germany bestowed upon him the prestigious Order of Merit of the Federal Republic of Germany. Dr. Dingwell is a member of the Royal Society of Canada, the Academia Europaea, and the German Academy of Science and Engineering. He has held office in numerous national and international societies, most recently serving as president of the European Geosciences Union. We are honored to welcome a distinguished alumnus of the Carnegie Institution as our speaker tonight. Ladies and gentlemen, please welcome Dr. Donald Dingwell.
Good evening. It's a delight to be finally at P Street. 30 years ago, somebody said, you should go to P Street. They have an annual lecture there. I never made it because I didn't have a tie at that time. And it's been 30 years, and I'm here. So I'm honored. When I arrived at the Geophysical Lab, just to take a few seconds to reflect on that, I was quite shocked. People at the Geophysical Lab, in particular Bjorn Meesen and Dave Virgo, sat around all day and just thought about what they'd like to work on. They could work on whatever they wanted to work on. Whenever I, coming from Canada, would say, we should work on something which is related to ore deposits in Canada, they would shake their heads and look at me and say, we do basic research here, Dingwell, basic research. You're allowed to do whatever you want. I guess that's when I was infected with that idea. And to be honest with you, working 30 years later at the European Research Council, it was nothing other than that simple statement. Let the world's best people do what they want to do most. And through this cloud effect, you'll probably get the benefit from researchers that you need to take you forward. Now, let me stop talking about the European Research Council and my own history and jump into the subject at hand. I called the talk Dancing on a Volcano, or the Dance on the Volcano, 25 years of first ascents. Of course, that was a blatant attempt to get as many people into the room as possible, and I see that it worked real well. So I'll try to remain scientific from here on in. Just a reference to the expression dance on a volcano. It's had many reincarnations in the artistic world, as you may know, one of which is a Led Zeppelin song, which you may know, or no, was it Genesis? But actually it's an expression dating back at least 100 years, referring to the First World War at least, perhaps going back further than that into the times of Goethe and so on. It's a basic philosophical consideration that we're on a very fragile basis of civilization at times, and that we need to work every day, every week, and every month to make sure that that basis of civilization pulls us back from the precipice. This is relevant today as it has ever been in the past, and in 2014, the 100th anniversary of the First World War, it's a great thing to reflect on as we go forward, Mr. Ambassador. So let me jump into the topic of the day. I'm going to talk to you about volcanic eruptions, and what I'm going to tell you is something you can only hear from about 25 people in the world, because there's only about 25 of us crazy enough to work at it from this point of view. And the point of view contains one word which is essential, is what brought me to the Geophysical Lab in the first place: experimental. Now, if you had said you were an experimental volcanologist 25 years ago, if you told me you were an experimental volcanologist 20 years ago, I would have smiled and just thought, well, there's another one who probably thinks that he knows what's going on, but it's impossible to do that in the lab. What's happened in the meantime, in about a quarter century, is that it's happened. If you go to a volcanological congress today, and believe it or not, there are thousands of people who do, then you will see days and days of experimental volcanology talks. And it means that volcanology, alongside all of the other earth sciences, whose reincarnation in an experimental sense began in this city about 100 years ago with the creation of the Geophysical Lab, the Carnegie Institution of Washington, that this transformation into a modern discipline has now also conquered volcanology. Now, volcanology was the home to the most beautiful and exquisite observations that somebody could stand up here and give you. It's really spectacular what happens physically in a volcanic eruption. Never ceases to inspire first-year physics students when I explain to them the beautiful playing field of classical physics that takes place in a volcanic eruption. And so it was one of the last fields which surrendered that complete dominance of observational character, and now has, of course, like all other fields, a strong simulational character, the theoretical character which goes along with that, and now, finally, the last piece of the puzzle, the experimental character. Let me jump into the story of how experimental volcanology took place and was created, and one path through that story. If you think about a volcanic eruption in the simplest of senses, and this comes from a successful European Research Council grant that I obtained, so it must be good stuff. And one of you in this room, I think, might have seen this before. You see, I've stripped it down to something which is very, very, well, so simple that it must be a simple philosophical point, and that it is. I worked on this diagram in my proposal more than any other diagram. It took weeks to get this right, believe it or not. We have the lithosphere. Residing in the lithosphere are regions which are hot enough that a lot of the Earth is molten down there. By virtue of being molten and the dissolved gases, these things are very low in density. So they have a fundamental driving force in the Earth's gravitational potential field to go up and not down, because the liquids are less dense than the rocks they come from, at least near the surface of the Earth, where volcanoes erupt. You have the eruption, which I've simply drawn through as a red stripe through the landscape. It's a point and a place in time, and what occurs is that a piece of the lithosphere, because magmatic systems at depth are a piece of the lithosphere, is suddenly, very suddenly, ejected out of the lithosphere and over your heads. And so you always have a bit of rock over your head. Never forget, there's always some ash up there. There's always a piece of the lithosphere over your head. It goes into the biosphere, it goes into the hydrosphere, it goes into the atmosphere. And it has consequences for all of these systems that we're just beginning to understand. The most dramatic things, and the ones that are being understood first now, are the atmospheric effects. And this is also because of the civil aviation crises that we've had in recent years, going from single jets, which almost crashed in the last 30 years, to shutting down airspace and economic losses of hundreds of millions for individual airlines in Europe in the wake of the Eyjafjallajökull eruption. So the eruption, if you will, is the way that the lithosphere speaks with the other spheres on the surface of the Earth. And inasmuch it's not just about the eruptions themselves and who they kill or how much infrastructure they destroy, but it's a fundamental character of the Earth system. And I firmly believe that ash in the Earth system will give us a lot of secrets to the way that the Earth has evolved, which we can't imagine yet. It's hard to get solid Earth scientists who want a decent density and a decent size of rock in their hands to get excited about ash particles that are 50 microns in size. But atmospheric sciences love them. Now, the problem, of course, is also hugely important from a civil protection point of view. And what you can see here is the statement which had been recently made that about 500 million people are lying close enough, or standing and working and sleeping close enough to a volcano to be immediately impacted by the near-field effects of larger volcanic eruptions. 500 million. That's a significant fraction, more than 10% of the world's population. You can also see the distributions of volcanoes. It's been referred to by President Meserve, and I won't go into it in any more detail. It's not a random distribution. It's one whose distribution we more or less understand, although not completely, since the advent of plate tectonics in the 1960s. If you look at civil aviation numbers and you look at the growth rates, which you can see in this table, divided up for regions of the Earth, then you can see the average growth rate is enormous. You know that anyway. You know how cheap it's become to fly. You know how many planes are in the sky. Tens of thousands of people over the North Pacific corridor every single day, flying, if you fly from the west coast to Japan, over an unbroken chain of volcanoes, all the way from Alaska to the Japanese islands. Unbroken chain. A slice through a great circle of the Earth, which therefore the plane takes to have the shortest route. If you look at how volcanoes kill, I once called this slide 15 ways to leave your life in a volcanic eruption. It's a complex problem. There's no way that I'm going to stand up and give you the answer for fatalities associated with volcanic eruptions or how we're to mitigate that. Things here range from literally being struck by volcanic lightning at the bottom, which apparently has happened, all the way up to indirect effects at the top, which sounds very ominous. And in the middle there, you see tsunamis, everybody knows about in the meantime, volcanic mud flows, and being buried by volcanic tephra. All kinds of things are going on. This is one of the messiest displays of the fact that the Earth is a dirty place and that real observational science, natural science, has to revisit that theme again and again. Now, our philosophy of how we do experimental volcanology is to really go back, strip it down, make it as simple as possible. The gift of being, or the talent for being an experimental scientist, is not to be good with your hands. That helps, Lord knows. But it's to be able to design experiments in a simple enough way that the answers that you will get from the experiment are very conclusive and very unique, so that they can tell you something. So defining the question that can be answered in an experiment is the real gift of experimental science. So it's actually a philosophical gift and not a practical one. I think we need to tell our students that again and again. In our laboratory experiments, the third arm, or the third leg of the stool, if you will, which has come into the game, we try to strip the system down very, very simply. I'll show you in a moment a simple one-dimensional scale of what we think is important in volcanic eruptions. This I will not talk about, and I may disappoint many by not doing it. This is volcano monitoring. You can see here a very low-resolution reproduction of a cartoon from the internet. I do all of that to make a point. I'm a long way away from volcanic observations and volcanic monitoring per se, but yet this is the big business of volcanology. This is where almost all the money goes. And when I say almost all, I mean something way over 90%. This is because there are volcano observatories all over the earth with lots of staff and lots of equipment. Volcanoes are not particularly nice about equipment that you put on their slopes. They destroy them regularly, and there's a lot of turnover costs in volcanic monitoring. Yet this is indeed the ultimate observational base upon which the advance of volcanic studies will be made. All we are doing when we are doing experimental work is trying to put scenarios behind the interpretation of signals which we have from volcanic monitoring. So bye-bye volcanic monitoring. It's a huge business, and it occurs in very beautiful places to visit. Now, this is my one slide in German to pay tribute to the fact that for the last 26 years, every cent that I've spent has been either European or German, and a lot of the equipment that you're about to see was set up especially by support from the Free State of Bavaria, which has had a very, very liberal attitude, and which was also strongly influenced by the workings of several individuals which had a strong connection to the Carnegie Institution's geophysical lab. What I have here is a simple one-dimensional plot that we don't really believe in anymore, but it helps us to strip out the processes one from another so that we can investigate them individually and then in chain reactions in our experiments. At the bottom I have saturation in German, nucleation, growth of bubbles, foaming of the system, very important because foams have rigidity, solid-like behavior, they have elastic moduli, they have a shear modulus, and therefore they will resist deformation by elastic response. That's why your foam stays on your bathtub in a transient, rigid state for a long time. And then fragmentation. Now you probably know what rigidity is, what foaming is, what bubble growth is. All happens more or less with various materials you use in your home. Fragmentation sounds a little weird. It sounds, well, maybe like a bag term. 20 years ago, it was a bag term. What I mean by a bag term is it was something we stuck in there between the world we knew very well from high-pressure experiments, which was highly viscous liquids with crystals and bubbles in them in a continuous flow to the surface of the Earth, and on the other side, dirty, dusty gas, as we call it, blowing out of the volcano. These are two very different states of nature. And yet, all that happens between the suspended flow and the dusty gas which comes out at the top is fragmentation. So one of the things that experimental volcanology has done in the last 25 years is taken this word from just a phrase used, a bandage used to describe this transition with no physics in it at all, to one which we now describe very well, and I'll show you in a minute. Now, all experiments need to have the hope that you will get at an answer, and therefore they need to have a premise that you're trying to test, an hypothesis of what might be a physical mechanism. And this is the physical mechanism that we're going after here. 1989, I sat down with a nice Australian lady, and she convinced me to put a paper together that would claim that we had solved the riddle of volcanic explosions, of explosive eruptions. I said to her, Sharon, you're quite mad. Nobody will believe us. We're not volcanologists, and we've never published on volcanoes before. Nevertheless, she won. We put it in the paper. It was 1989. I was right. For 5 years, 6 years, I can tell you exactly how long it takes to get something done in terms of a paradigm shift in geosciences. By 1995, all of the grandees of volcanology, who had done all that exquisite observational work over 30 or 40 years, which I had been somehow neglecting or skimming over with my generality, started to swing around hard to support our point of view. This was what we were talking about. This yellow line is nothing more than the glass transition. The glass transition is something that every Coke bottle has been through. It's something that every float glass window pane in this building has been through. And it's something that every explosive eruption on Earth has been through. In fact, it is the reason that the explosions take place. The simple observational fact is that volcanic ash, one of the most common products of explosive eruptions, consists in most cases of a matrix of broken glass. It has knife-edge shards with surfaces that represent former bubble walls and so on and so forth. It's as if somebody took a hammer or a mortar and pestle to a rock and crushed it up and produced broken fragments. Yet the flow which caused this has been a viscous system, multi-phase system, flowing up a plug, flowing up a conduit, and pouring up at a certain point until it can no longer flow. And because these silicate liquids that we're looking at depth flow in the beginning and break in the end, we can be absolutely conclusively sure that they've gone through the glass transition. Now, when we first proposed this, people said to us, wait a minute, the glass transition here is a low temperature feature. We know they make Coke bottles at the glass transition. Everybody knows that, and they certainly don't go to 1,500 degrees Celsius or 1,200 degrees Celsius to do it. It would cost way too much money. They go to 400, 500, 600 degrees Celsius. The key point of this diagram is that it is time scale on the vertical axis, fast and slow, versus temperature, hot towards me, cold towards the other side, an Arrhenian reciprocal absolute temperature horizontal scale. And you can see the yellow line is not vertical, it's not horizontal, it's sloped. It depends, and the temperature of its occurrence depends upon the time scale of the process of deformation. And so by doing things quickly, you can force a solid-like response. It's a classic viscoelastic material. If you have silly putty, if your children or your grandchildren have played with silly putty, you can demonstrate it to anybody on this planet within a minute by taking a piece of silly putty in the hand, slowly deforming it, pulling it, watching it viscously respond, and then as silly putty beautifully demonstrates, pull it quickly, it snaps apart, and you have two broken surfaces that look like they've been broken with a hammer. Let me show you one glass transition. It's a slow transect of the glass transition. If I can get my video started here. Here we go. This is Aetna. This is a lava flow on the side of Aetna. Many of you may have seen this kind of a video before. You can, if you don't look at the details, but you just look at the whole surface of the flow on the top, you get the clear feeling this is a flow. It's sticky, but it's flowing. The whole thing is flowing as a body. Inside there's a viscous core. But then if you look at the flow front, and I mean, tourists literally walk up to these things and look at the flow front. That's how slow these things are. You see blocks falling off the front. These blocks are cooled blocks of what was a viscous flow at high temperature. So you've gone from a viscous state in the interior to blocks on the outside. You have passed the glass transition because there is some residual glass left in this material. It's not all crystallized. Now, this is a very benign transect of the glass transition. Nobody is going to be killed by one of these lava flows unless they really have bad luck, okay? But there are other transects, and this is the one place where I step out of my talk and do what everybody hates doing, which is to try to activate a video that wouldn't embed itself. And, 2014, go for it. This is another transect of the glass transition.
Une coulée pyroclastique 10 fois plus violente que les autres se déclenche.
Excuse me, I've got to get it onto the projected screen, and I don't have it on the projected screen. I was going to show you a pyroclastic flow coming down the slope of Mount Unsen, which shows rock which has exploded and produced a huge ash cloud behind it, but I don't see how I'd be able to get it on the projected screen now because I'm not fit enough. Anyway. The same thing you see when you see a large ash cloud rising to the surface and rising up into the 10 kilometer transition into the stratosphere is the glass transition. It's the production of small ash particles as you move across the glass transition. Now I'm just trying, my mouse is over there. There we go. Now I got my mouse back. Okay, back to the presentation. So the only good news about not having seen that video is it was in French anyway, so. Oh, what do we have here now? Et voilà. This is the top of a dome in Kyushu in
Une
southwestern
coulée
Japan.
pyroclastique 10 fois plus violente que les autres se
Watch
déclenche.
this. All of this ash, this is not
En
dust
quelques instants,
kicked up
la
by this
vallée est
flow going down.
submergée.
This is new dust. This ash produced from something that was a few tens of meters of solid rock, no more. And of course, this is the famous eruption of Unsen from the early 1990s, in which about 45 people were surprised because this flow jumped an intermediate ridge, shot over the other side, and killed, amongst others, the most famous volcanic photographers in the world, Maurice and Katja Kraft.
Quand les caméras de la télévision arrivent sur place, Maurice, Katia et
You will
41
see now
autres
in a
personnes
minute that it loses its
sont
driving force, and within a second, look. So there's nothing in there. There's a lot of gas and very little ash, but it's very hot. There are 4 ways one of these pyroclastic flows can kill you. You can be killed by the temperature, burned to death. The vegetation is burned with a knife-sharp boundary. Beyond it, nothing happens. You can be asphyxiated because the ash is fine enough that it's autopsied out of the lungs of animals which are caught in people. You can be buried alive by the ash, and you can be killed by blocks the size of this room, which are inside the ash, which is, of course, completely opaque, even if it weren't hot. If you've seen pictures of the World Trade Center, to bring a painful point home, of shop windows where the dust cloud goes by, the debris, then you get a feeling of what it would be like if you could survive one of these flows. Now, here you see the fundamental property which lies behind all of this glass transition. It's the viscosity. It's Newton. It's the internal friction. That's what he called it, the internal friction. Beautiful phrase. And the internal friction of these liquids is highly dependent upon their chemistry. If you look in the lower right, you see viscosity versus reciprocal temperature. If you look in the upper left, you see the chemical compositions simplified in terms of total alkalis versus silica. This is what the Earth gives us in terms of the range of chemistry of these rocks. And on the lower right, you see what is almost 25 years of experimental work to produce a general model of viscosity versus temperature for these liquids. If you look at the vertical scale, it's log base 10. So you see there's a huge range of viscosity as a function of temperature and as a function of chemistry at any given temperature. Those are Newtonian viscosities. It means no matter how quickly or slowly you deform, you always have the same coefficient, which tells you how much stress you need to push it. But even that breaks down if you go to extreme conditions. And if you go to the glass transition, the following happens. You see in the upper left-hand portion of each of these curves a flat plateau. As you go to the right, something very scary happens for a rheologist who's trying to keep his materials under control in the lab. You hit this cliff and you just dive off the cliff. The resistance to flow disappears under your feet, so to speak. It's a runaway process in most kinds of rheological measurements. And so this is the onset of non-Newtonian viscosity, to put it in a very gentle way. It's actually shear thinning. And each of these experiments, the last data point on the right, was terminated by a snapping of the liquid, a snapping of the liquid. So brittle behavior of what was, nominally speaking, a liquid. And that's what happens when glass is brought to the glass transition. Now I'm going to take you through 2 transects, one slow and one fast, to put them very simply, which will show you how we do our experimental work. They are both doing the same thing. As you can see, they're both located on this yellow glass transition curve. Let's look at the fast ones first. Fast ones take place in this device. This is sitting in the basement of the Theresienstrasse 41 in Munich. It's between all of the Pinakothek museums. If you're ever in Munich and looking at the wonderful 4 museums of art which are downtown in Munich, you're only a stone's throw from this experiment. Above it is a lecture theater, but I'm not sure what seats are actually above the experiment. If you look on the left and on the right, you see something that looks symmetrical there on the left-hand side. You see 2 tanks. They're about 3.5 meters high. These are the atmosphere. These are stainless steel tanks, not cheap, but at least they don't rust when we throw ash into them, which is an advantage because you don't want paint particles or rust mixing up with your products of your eruption. If you look at just below the large tanks, you can possibly imagine seeing a very small cylinder, which is the magma chamber. That's where we're cooking and pressurizing our magma. So we literally go to the field, take a piece of a block from a block and ash flow, which explains itself, which has just fallen off the mountain in an eruption. We pack that stuff up. Sometimes it's even still warm by the action of steam through the deposit. It's quite striking when you turn over a rock and it's hot on the other side. You sort of look up at the volcano immediately. Anyway, we take these samples back home. We drill them out to a certain length and diameter. We pop them in an autoclave, a pressure vessel of a kind that was developed at the Geophysical Lab in the 1950s already, slightly modified by Tuttle and Bowen. And you see on the right-hand side, it's glowing red hot. This is the bomb, the autoclave, which is holding the sample before it explodes. How does it explode? We don't put dynamite in there. We don't shoot at it with a rifle, which has also been done by some of our colleagues in experimental volcanology. It wasn't particularly helpful for getting the field further in terms of acceptance. But they were right, of course. They were just saying any source of energy would do. What we do is we simply take the pressure away. It couldn't be more simple. We simply blow the pressure. How do we do that? We have membranes that are sitting between the high-pressure bomb and the atmospheric tank, and we let them fail due to a slight pulse in pressure that we give to an intermediate diaphragm. The bottom line is the sample sees nothing, the membrane breaks, and then explosively and at high speed, a decompression front rips into the sample and actually tears it apart due to the pressure gradient. What is the driving force for the failure then? We have bubbles, gas bubbles, with high pressure gas in them in the sample, as we do in magma. And once you take away the confining pressure, you still have all of the vesicular pressure stuck in the sample. And these bubbles can be as finely distributed as Coke when you shake it up. Every single one of those bubbles wants to blow because it has more pressure on the inside than is sustained on the outside. And they do. And so we can actually produce volcanic ash in the lab. We're very proud to say that we were the first people to reproducibly do so. You can see some of the specs on the right. I won't go into it in detail. Basically, then, we have a bubbly magma, a diaphragm, and air above it. And if we go to the right-hand side, we have this bubbly magma where you can now see a velocity of a front. We call it a fragmentation speed or a fragmentation front, which rips into the sample over time and produces ash or doesn't produce ash, depending on the conditions. And here you see in more detail than you can probably depict from the back of the room, various arrangements. We've played with this device now. We've had it for 20 years. You can imagine all the things that we've screwed on the side of this thing, and yet there's still much more to do. But here you see three different scenarios. One of them is the threshold, one of them is the speed, and one of them is a word or two about permeability. And here's what's happening when one of our samples goes up the chute. Let me get my mouse back. This is a sample of dome lava under pressure. Here it's in plexiglass, just so you can see it. Exactly the same thing happens at 1,000 degrees Celsius. We know from an analysis of the fragment. So there it goes. You can see there are sort of what I could call, not knowing whether it's a word or not, a subhorizontal crack. I was once asked in a review, what's subhorizontal mean? Almost horizontal crack. And it comes in at regular spacing. We think we understand why the regular spacing take place. And you can see chips of this geometry in Volcanian eruptions of Montserrat in the field. If we look at the right-hand side, you see a sample where we allow a little bit of viscous deformation. It's not quite solid, and it's actually much closer to the case for most eruption of volcanic material. These are analog materials, but you can see, whoops, didn't want to do that. Try to get back, yep. You should be able to see here material which has some viscous response, see? But not enough to prevent it from ripping apart. Now this begins to look like products of basaltic eruptions, low viscosity eruptions, which have some deformation. And now this guy's going to come back down again. Here it comes. Isn't that exciting? I went too far. I want you to see it hit the bottom. And you see one further fundamental point about these materials. As soon as it hits the bottom, it's still somewhat liquid, somewhat viscous. It deforms, spatter, ladies and gentlemen. It's found all over Hawaii. Now I want to show you what goes into the tank. This is all done with high-speed cameras, and it's quite a revolution to look at volcanic processes with high-speed cameras. Here comes the gas into the tank, which was over the pressure, and now here comes the rock. Watch how long this runs out. The fact that this runs out so long with a more or less constant velocity means we have a transient steady state flow here, which we can use to get physics out of these experiments. Speeds, energies associated with it, the surface created, and so on, okay? So when you hear the word explosion, I'm sure you think of dynamite or Semtex when you hear volcanic explosion, but these explosions run on for days. There's always been a bit of a paradox of why an explosion should run on for days. I'll say a word about it in a second. So what science can we get out of it? What numbers can we pull out of it? First thing we can do is say how much overpressure do we need for one of these things to blow up, to produce ash. And here you see how much. And it turns out to be dominated by one variable, the bubble content of the liquid. And the bubble content of the liquid is the porosity. So on the left-hand side, you have solid rock. On the right-hand side, you have foams of up to 80% porosity. Okay, pumice. And you can see all the data points. You can see many colors. To our great embarrassment as petrologists, people who spent all of their lives describing the chemical variety of rocks, chemistry plays no role. No role. You see all of the data points lie on one line. At this point in the evolution of a volcanic system, the vertical scale is the physical tensile strength, if you will, goes from about 30 down to about 3 megapascals. At the point of the eruption and the explosive behavior of these systems, it happens so quickly, you've switched off all chemical reactions. No doubt chemical reactions have brought the system to the point where this is about to happen, most importantly, degassing and bubble growth. But that's now behind this system. Now it has to face the rapid decompression event, sometimes caused by itself, sometimes caused externally by a landslide, and when it hits that event, it happens so quickly that it's basically physics left over. Therefore, chemistry doesn't count, but physical properties, such as the number of bubbles in the material, do count, because that's where the overpressure lies. Fragmentation threshold, we called this. We had to come up with a name, and it sounded like a good name. You always know you're getting somewhere in science when you have to invent words, right? If you look at this plot, it's the speed of the process. How do we do that? We have dynamic pressure sensors. You can see up in the high left-hand side. You have a dynamic pressure sensor above the sample and one below the sample. So we're simply measuring pressure over time above and below the sample. And the time between the decompression hitting the top of the sample, which we see in the first sensor, and the decompression hitting the bottom of the sample, which we see in the second sensor, is the time it takes to evacuate that sample out of the tube. That's a simple approximation. And you can see here the speeds. Don't worry about the diagram too much. It's pairwise signals from the upper and lower sensor, as you can read. But look at the speeds, 90, 30, 20, 15 meters per second. I don't know what you think about those speeds. If you think they're fast, if you think they're slow. The acoustic velocities, the speed of sound through these materials, is kilometers per second, because these are behaving in the brittle state, solids, and all rocks are having velocities in the order of kilometers per second. 15 meters per second? That's dead slow, dead slow. So the process which effectively rips these materials apart involves more than simply sending the pressure wave through the sample. It involves deconstructing this material in a mechanical sense. We're talking about a world of failing bubbles with characteristic sizes and characteristic crack lengths that have to be achieved before the material is completely destroyed. The other point is the speed is so low. How can I get excited about a low speed talking about explosive eruptions? This speed is so low that we know from completely other sources and methods from petrology that magma can come up from depths within the earth at that speed. 10 meters per second is completely normal for an ascent rate of magma during a volcanic eruption. Why do I say that? Now you have the possible explanation of how you can have a volcanic explosion which runs on for 72 hours. Because your reactants, in a physical sense, are being sent to the site of the explosion, the fragmentation front, at the same speed that the fragmentation front is eating its way in to the column of magma. So in particular circumstances where those two speeds match, you can rattle on for as long as magma keeps being sent from below. The system can run out shallow and stop the eruption. Very important question. When does an eruption stop? Perhaps the most important question in terms of civil protection and mitigation. Starting, we may or may never get that right, but when we got one going, we know it's going to stop. The question is when, and what do you do? Do you evacuate, and so on? So it's probably the duration of these eruptions probably depends upon whether the magma supply rate, sounds obvious in a way, is matching the fragmentation rate. If it shallows up, you get a dome coming out at the top, which is the volcanic plug, which is not broken at all. It's sitting on top of the mountain, still intact. Happens. Or perhaps you get a Vulcanian explosion where it goes down deep, where there's no magma movement towards the surface at all. There's just an explosion, bang. And then it's, as you would imagine an explosion, I can imagine myself, that the material is simply excavated like in a rock quarry. In both cases, the fragmentation front is moving. In this case of a Plinian eruption, the biggest ones we know, the super eruptions, how do you get thousands of cubic kilometers of solid rock out of the earth, we believe, in days and weeks? Probably it's this dynamic equilibrium between these two processes. Gas is trying to get out. In fact, gas is the problem in volcanic eruptions. Basically, volcanic eruption or volcanic systems are degassing all the time, 24/7. It's a question of getting high-pressure CO2 and water out of the earth. In fact, you can look at eruptions as industrial accidents. It's these volcanoes which, for some reason, are not able to degas sufficiently quickly, such that the gas on a particular day, in a particular hour, in a particular minute, decides to take the mountain with it on the way out of the volcano. We talk about failed eruptions, but we should probably actually talk about eruptions as failures of the system. You can see on the right-hand side a plot versus permeability, and you know I'm paddling in this direction. Here we have the threshold energy, which is the PV energy of the gas in the bubbles, and we have the permeability. And you can see it's a constant value for the left-hand side of the right-hand diagram, and then it begins to run away and become dependent on the permeability. Dependent on the permeability of gas, that means that gas is flowing out of these systems, and therefore it's playing into the result. But it only does it at the high permeabilities. So we know that there's now a balance between the speed of degassing, which is the gas getting out without the need for fragmentation, and the speed of the fragmentation itself, which we've just measured, turns out to be fairly slow. So a few words about the slow experiments. They have the huge advantage that you can measure a lot more stuff because you're not waiting to do it on the fraction of a second. And there are, in fact, slow eruptions, which go from fluid supply to brittle failure at the surface of the Earth. They last for years, some of these eruptions. There are lava flows flowing down mountains in Guatemala as I speak that you've never heard of. They're still flowing. There are lava flows, Cordoncall in Chile, where our colleagues went there a year ago, where they can stand, but they have to take time-lapse photography. They can stand in front of the flow. It's not hot enough to glow, and it's not moving fast enough that you're constantly seeing rock falls off the front of it. You could almost believe it's not erupting. You know, you could almost think you would tent there some night, and in the morning realize that the lava flow is a little closer to the tent than you thought it was. It all feeds into seismicity, because when rocks break, they make noise. When anything breaks, it makes a noise, and when lava breaks, it makes a noise as well. When we go to the boundary and we look carefully about what's happening because we take the time and do it slowly, we see that we have three effects that we have to worry about. We have a viscous heating effect. We have a structural effect that I've already described to you, that the liquid is ripped apart, and we have, of course, suspension of particles, which messes up the rheology. The viscous heating effect has now been done experimentally. It's relatively easy to do. You simply ram thermocouples into a sample, squeeze it at particular rates, and see how much viscous heating you obtain. The samples look barrel-shaped afterwards. There's a certain degree of homogeneity of the bulk deformation, even though, as you see, these samples are horribly heterogeneous, having crystals and cracks and bubbles in them. And here you can see the climb of temperature. Not easy to measure a half a degree Celsius when you're at 500 or 600 degrees Celsius in an actively heating system with a feedback control on temperature, but it can be done. And we can see very clearly where viscous heating steps in. Viscous heating is important because if there was enough viscous heating, nothing would ever break. If pushing things harder meant that the viscous heating would raise the temperature of the system, then the rheology of the system would fall, the things would be more fluid, and they just continue to flow. And it turns out that there is a balance between where we expect that viscous heating will occur first, and therefore we avoid the fragmentation, and another range of temperature. You can see the cross of slopes, the green slope representing that of the onset of viscous heating, and the blue slope representing that of the onset of failure due to the relaxation time of these systems. And you can see if the onset of heating destroys your Newtonian field first, then you will not fragment on the left. Whereas the onset of failure, if that intercedes and goes first before viscous heating becomes important, then it breaks. We now think viscous heating actually allows these flows that are flowing tonight in Guatemala to go further than they otherwise would go. And of course, the noise is made. And Jan Lavallee, a student of mine now at Liverpool, deserves special note here. And that is that if you look on the right-hand side of this diagram, you can see three things plotted. You can see in the middle the temperature beginning to climb. You can see at the top the relative strength of the rock at three different applied pressures becoming weaker as we squeeze it harder because it's beginning to fail. And you can see, despite the viscous heating in the middle and the bottom, you can see a nonlinear rise. This is the number of acoustic emissions and the cumulative energy associated with them as time goes on. So this stuff, a rumble begins in this material and it leads up to a failure at the end. And this is, if you will, analog to seismics. It's not seismics, but it's analog to seismics. And it gives hope that we may be able to understand from acoustic measurements of volcanic mountains when things are about to go. I'll jump a little bit ahead. We get all of the particles out of these experiments. We get all the ash. We're the only people in the world who really get all the ash. Everybody else is working on analog materials such as corn syrup and glycerol and all kinds of cool things where you can visualize experiments at room temperature or near room temperature. Great stuff, very valuable stuff, a lot of fundamental physics and a lot of fluid dynamics being done. But nobody gets the ash afterwards. You do the experiment with low temperature, low viscosity liquids, and you get a pool. Your product is a pool of liquid at the end. Here we get the ash. So we can do grain size distributions of the ash, which is what you see on the right. Cumulative curves showing the total cumulative grain size and the actual individual bins showing grain size distribution. And we can see that if we go to higher pressure, the conclusion drawn from this diagram, if we go to higher pressure, then we get finer particles. If we go to higher temperature, we get coarser particles. We suspect that the higher temperature is allowing some viscous deformation of the system, which is allowing us to be robbed of the energy that we need for fragmentation. A lot of details I won't bore you with. Look at this curve. When particles come out of our experiments, I said that we were quasi-steady state, but of course, over time, the whole thing slows down. The energy of the last particles coming out is not those of the first particles. So you get a blast, and then you get ejection velocities which slowly slow down over time, and that's what you're seeing plotted here as a function of fractions of a second particle velocity, simply from those videos. If you go to a real eruption, if you look at the top here, you see what looks like a mess. These are measurements from Stromboli, where we can watch the particles blowing out and where image analysis software now allows us to count the parabolic trajectory of every single block that comes out of the volcano. Spectacular work by Jacopo Tariucci. If you look down at the bottom, it's two slices taken out of the top. As you can see the same dependence of velocity of particles on time as we see in our experiments. It is more or less the same process. So, to conclude some of that, before showing you a last few speculative slides about work in progress or not yet begun, we can see that we have frontiers facing us now on frictional melting in conduits. I'll show you that in a moment. The idea that by frictional melting, by viscous dissipation, that you can actually reheat magmatic rocks. It sounds counterintuitive. A word or two about cyclic fail and heal cycles, because these magmas had the property, once confronted by a seismologist, how do I get volcanic earthquakes in the same place, looking exactly the same, again and again and again and again? It doesn't make any sense in terms of modern seismicity or seismology, because rocks break and then they're broken. How can you break them again? I said, magmas can be broken again and again and again. Why? Because they're liquid. You relieve the stress, they have a chance to heal. You break them again, heal them again, break them again, heal them again. And we have such things going on in nature. We speculate that drumbeat earthquakes in Mount St. Helens are exactly that. Ash aggregation, I'll say a word or two about it, and then I'll show you a last spectacular video of volcanic lightning, as President Meserve was nice enough to refer to earlier. This is frictional heating experiments. This is a friction press. These kind of things are used for friction welding, but there's a whole branch of science which investigates what happens when you take two pieces of rock and you push them together with a high degree of rotation. This is melt produced by frictional melting of two pieces of dome lava. And when you first see these experiments or hear about them, you think, oh my God, it's the most unconstrained thing in the world. How can you do science looking at a friction press? But actually, in the same prejudices that we had for the development of the beginning of experimental volcanology. They are also now overcoming the prejudices against that branch of research. And we now believe that there is frictional heating going on in conduits. If you go to the top of a dome of an active lava, which I can't recommend, it looks like a glacier. There are crevasses and there are spires all over the place, okay? It's actually flowing downhill on the sides, very, very slowly, like a glacier. Yeah? And there's strain localization. You have fault surfaces as high as a house right in front of you, where the lava has decided all of the strain is going to happen right down this fault, essentially, where friction can be maintained rather than deforming the bulk. Just a couple more pretty pictures and then I'm done because I'm sure I'm running out of time. These are the latest results from Liverpool. Don't be distracted by the black strip in the back. That's a slot in the furnace. It took me a while to figure that out when I got this video sent to me. That's not the sample. We're not doing that to it. The sample is the two large cylinders that are light yellow. And systematically, cyclically going back and forth like this and seeing how much it takes to do this. You know, as a function of contact time near the glass transition. And you see the growth in the amount of stress that it takes to pull these pieces apart as you leave them longer stuck together. So we're really getting near the physics of what this fail-heal cycle might be in volcanic conduits. I'm going to skip over a lot of the stuff on volcanic ash in the atmosphere because the time is running out. I just want to show you what I think is the ugliest diagram I've ever seen in my life. It's by Alan Roebuck, and I say that as a tribute to him because what happens when volcanoes toss this stuff into the atmosphere is really ugly. You have ash particles, finely divided glass, beautiful catalytic surface. Together with that, you throw up sulfur dioxide, hydrogen bromide, hydrogen chloride, hydrogen fluoride, CO2, a little water to get things going along. You toss all this up into the stratosphere, and as you know, Pinatubo being one of the most recent examples, doesn't belong up there. As you know, when you fly, it's awfully dry up in the stratosphere. You fly at the edge of it. And so you literally overload the Earth's stratosphere in water. Sounds impossible. With one eruption, with CO2, with SO2, and they have residence times of years, and then they slowly fall back out of the atmosphere. This is the life cycle of ash. Can you believe it? There are only about 20 articles on this. This is a burgeoning field being created by people like Pierre Delmel, and that thing over there, which looks like the climate change analysis, is actually what can happen to ash once you've gotten it out of the volcano. Well, let's say the volcano is a simple story. Let's just worry about what ash is doing when we have it in the atmosphere, in the hydrosphere, in the biosphere. Good grief. So we're developing the last stage of the work that I want to show you about here is that we're developing reaction chamber now for looking at the reaction of ash with the co-erupted gas. Sounds crazy. It was all together in one rock. Bang, it got fragmented. But of course, as soon as you move temperature and pressure, equilibrium shifts, the ash particles, still hot, are now being exposed to these nasty aggressive gases which they used to have inside of them. And they start to eat their way into the surfaces of the ash particles. And we believe that up to half of the sulfur which comes out in this cocktail can actually be lodged into the surface through diffusion and through precipitation of crystal phases and never gets out of the volcanic deposit. We call it sulfur, just to be controversial these days, we call it sulfur sequestration in volcanic eruptions. Literally, and got it published. Okay, I'm going to jump through. I just want to show you a video now about distribution of ash. Don't be comforted when the meteorological office in England or in the US tells you that they can predict how ash is distributed in a volcanic eruption. They can't. Yeah? They can't. They usually use codes which are created for a completely different purpose, perhaps for Chernobyl or something like that. They can predict it, but there are effects which they're completely missing. And one effect that I want to show you is in this video. If you look carefully, there are 3 circles. Each one of them will show you something happening just near Eyjafjallajökull as it was erupting, and you get the picture right away. The first one, see it? The second one, you see it? Third one, boom. These are falling out of the sky right next to Eyjafjallajökull. By the time the third one fell, you probably saw it was a large clump of stuff that fell, and when it hit out of its own weight, the impact blew it into, 100 or 200 particles. These ash particles are aggregated to 100 or 1,000 times their original size. It means their fall velocities and everything are completely unaccounted for in a sensible way in the modeling of volcanic ash cloud distribution. So there's a lot of work to do on how ash aggregates as well. Now, this is a long way from solid earth sciences, you say? I say no. The people who are best trained in solid earth sciences are just the people to try to cope with the complexity which these systems produce, even if it's over our heads rather than under our feet. So I'll go to my last slide. I made it, I think. This month in Geology magazine, a wonderful magazine. It's where everybody sends their nature and science papers that don't make it, which, as you know, this is being streamed, right, is a significant fraction of scientific advance in the world. Look on the right, and here we go. We had a problem with our video with these eruptions. We had flashouts in certain frames. And so when we were about to give up on everything, somebody said, let's speed it up by a factor of 10. And then it came. Now, I have no time to go into the details of what we think is going on here. There are basically two factors going on: a tribological effect, friction, as you can well imagine, probably jumps right into your mind. And then you have to get the field gradient set up so that the fine particles, which are differently charged from the large particles, will effectively discharge in this manner. This looks all the world like what's going on yesterday and probably today in Cordon Caul. If you go into the internet, you do volcanic lightning tonight, Cordon Caul, C-A-U-L-L-E, you will see unbelievable still shots of volcanic lightning which is coming off of that cloud, which is going up right now in Chile and spilling over into Argentina. I thank you very much for your patience. I've hit you with a lot of stuff. God bless.
We have some microphones in the aisle, and I'll welcome that anybody who has a question for our lecturer to come to a microphone and give it a shot. Please.
Hello, my name is Pablo Rodas. I am economist from the Inter-American Development Bank. About 20 years ago or 10 years ago, geoengineering was considered a kind of science fiction. But in recent years, because of all the problem of climate change, it's being considered more seriously. And between the different methods that have been proposed in geoengineering has been mainly two. One is to reflect this sunlight, to avoid this light to come to the Earth. And the other is try to replicate volcanic eruption. My questions here are three. Is it technically possible?
Yeah.
Because it has been suggested mainly for the Arctic and Greenland and for the Antarctic. Second, if is it possible, would you support this idea or not? And third, if you are called to be involved in a project like this, would you participate?
You know, we all bow down before economists these days. If I understood you correctly, you're talking about geoengineering and eruption in a preemptive manner. If that was what you said, I do not see how it would be possible. If it was that question, I've actually. To place ash in the atmosphere, which is otherwise not there, with the purpose of cooling the Earth. Yeah. Let's talk later.
Please.
Very quickly,
Yeah.
The unbroken chain of volcanoes in the Pacific Ocean, do they move as the continental plates move? And I know this is somewhat out of your sphere, but I'm very curious about that.
Yeah, yes, they do. The edifices move, they're tacked to the rest of the plate, and they move with the rest of the plate. And these are movements on the order of centimeters per year, and they appear not to have a major effect over at least the time span of active volcanism that we're talking about on the chemistry of what's coming out of these volcanoes. Of course, on geological time, it's a different story.
Well, we've had a fascinating survey of, we have one more question, please.
Has what you've found in the lab affected what people in the field are looking for?
Yes, the answer has many parts, because as you can imagine, there are many details that you can pick out of the results of these experiments, some of which we expect will be the things applied, and other things that people walk up to us at meetings and say, do you know that what you did in that experiment might have another way to be interpreted in the field? So in terms of the particle characteristics, yes. In terms of understanding the shape of materials which are fragmented out of the volcanoes, everything seems to fit. Where we hope for great progress in the future is on the seismic side, where eventually we may be able to do enough in the lab that people will understand how it can be applied to seismic monitoring. And although I don't want to say too much about it, this latest event with volcanic lightning has the advantage that if it's somehow correlated with the amount of fine ash in the cloud, then electrical monitoring of volcanic vents may be your best way of saying how much ash is coming out, the source function which is needed for modeling the distribution or the dispersal of volcanic ash in the atmosphere. Having said that, I'm sure there are many other aspects of the experiments that in time will surprise us as they are applied in the field.
So coming at it from a slightly odd perspective, from molecular gastronomy or from the science fair point of view, where we no longer want to do, baking soda and vinegar, could you use the corn syrup you mentioned to make your own lava at home? You said you didn't get the ash, but is there a way to do a home version of your experiments?
Certainly, certainly. There may even be descriptions of that in the internet. There is a laboratory branch of analog materials which uses what I would call simple materials. They're not simple molecularly, I suppose. Simple materials such as corn syrup, because they have very well described physical properties, including viscosity, and you can do the experiments in a range of temperature where you can observe it. So I wouldn't be surprised if you Google the idea of volcano in a kitchen that you would be hit with a number of suggestions of how to do it.
I saw an interesting a lecture about dedicated to global change, global warming, climate change, and they showed a pretty relentless rise in the Earth's temperature. I'm not sure by what exact parameter, but there were two significant deflections in that line, and someone asked after the lecture was what did those represent, and they said number one was Mount St. Helens, and number two was another significant eruption, perhaps you would know. And I know that's not the focus of your interest, but I guess it's related to your first question about the impact on climate change. And a second one, unrelated, is the lightning phenomenon that you're talking about, where it's well known that the reason why so many people died around Vesuvius is because it was such fertile. There's such fertile farmland around, grape-growing territory around volcanoes. Might it be associated with the nitrogen fixing associated with lightning, and at least partially?
Yeah. So you've touched, there's a few things in there, I think, probably more than just what I can see. Nitrogen fixation has been proposed to be a direct consequence of volcanic lightning. We're trying to get people from DLR, Deutsche Luft- und Raumfahrt, the people who flew the experimental plane through the ash cloud when Eyjafjallajökull erupted, trying to get them to build their sensors for nitrous oxides onto the side of our tank. We've been really slow in getting the chemistry of this stuff under control because I've had mostly a physical group that I put together. We expect big advances on the chemical side as we go forward. These spikes in the temperature record, I think there's nobody who disputes that if volcanoes were going off all the time, that they could compete with man-made CO2. But they're not, they go off incidentally. When they do go off, they certainly put dents in the temperature record over a year or two, as we heard about the year without summer from President Meserve, and as you see in modern day. So on the order of 1 or 2 or 3 years, volcanoes play a major role. The challenge is that they don't appear to have a significant flux compared to anthropogenic CO2 on a scale of hundreds of years, as best as we can say today. I can tell you there are active projects also supported by the ERC, which are still trying to do the inventory of volcanic gases around the globe. It's not so easy to do. Most of it is under the ocean.
Last question.
Thank you for your talk. I was interested in a line in your bio where it says, you've defended the interests of Europe's premier bottom-up, individual, excellence-based research program. I wonder if you could contrast science funding in Europe versus the United States.
Oh. This is not a set-up question. I have never received a grant from a U.S. authority, so I cannot do that, obviously, from first-hand experience. I was 2 years in this country, but the Carnegie was generous enough that I never wrote an NSF grant. So I can't do it. I know many colleagues who would jump up and be happy to do it for you. Just let me say about the ERC, it's bottom-up funding, which means that you can apply for anything, as long as it's ethical and legal, and we'll check the ethical for you. Yeah? It's enough money to give you all the freedom you need in almost any discipline, millions for a few years for people who are 2 years past a PhD. You have 25-year-olds walking around with $2.5 million in their pocket, figuratively speaking. This is changing people's careers in Europe because Europe recognized that it was overstructured in its research funding, that what people had to do in the work of applying for money was becoming outrageous. It's not for everybody, it's for the elite, it's for the top few percent of Europe. But for those people now, the idea is to give them the money and get out of their way for 5 years.
Well, we've had a fascinating tour this evening of a very interesting new area of science that our speaker has been spearheaded. And please join me in expressing appreciation to him.
Thank you.
I would like to thank the European Union, the Embassy of Switzerland and Austria for helping to sponsor this event. So thank you all for joining us. We're now adjourned.
Great, super.